This is a research talk about a new paper called The Mamba in the Llama. As the title suggests, this paper is about distilling and accelerating hybrid language models. This work was done by Junxiong Wang along with Daniele Paliotta. The work was also advised by Avner and Tree Dao at Together AI. I'm going to motivate this work by thinking about LLM agents. Let's say we have a language model and we want it to solve a very difficult task. For instance, let's say it's a coding agent and we want it to write a function for us. A lot of recent research has argued that the best way to go about this problem is to let the language model talk to itself. Let it try out different ideas, see which ones work, and recover from different mistakes. This will take a lot of inference time compute, but we have a lot of compute, so we can just throw it at this problem. I mean, if it can write complicated functions for us, that's definitely worth the cost. But there's something rather crazy about this strategy. As we let the model just babble to itself and generate more text, it's making the context longer and longer. This is all well and good for very simple problems, but when we're talking about really putting in full code bases into the model and letting it try out hundreds or even thousands of different tries, the inference cost becomes the bottleneck for having smarter agents. A really nice alternative approach would be to have an RNN hidden state. If we use a model like a recurrent neural network, in this model we only have a single hidden state that is remembering all the necessary information from the previous part of the conversation. If we can get this working, we can do much more efficient search and explore many more possibilities in this agentic world. I won't go into too much detail about how or why these recurrent neural networks seem to work very well for language modeling, or some of the recent advances that have made them efficient on modern hardware. If you're interested in this topic, I have several other videos, and I'll put some other links to recent papers in the comment section. What you have to know to understand this paper is that we'll be aiming to build a model with the following mathematical form. We'll have linear time-varying values, a sub t, b sub t, x sub t, and c sub t. These values will be created dynamically from a neural network, and they'll be used to compute an intermediate hidden state which we'll call ht. This value will then be used to produce the output value yt at every time step. The transformation in creating the yt value corresponds to a linear transformation of all the previous xt values that are fed into this recurrence. The key property to remember is that ht is representing the entire hidden state of the model at a given point in time and can be used to create every downstream value. We'll contrast this with the standard transformer model, which utilizes attention as its memory mechanism. The transformer equations can be represented in the following slide, where we dynamically create a qt, kt, and vt intermediate value, and use these to compute attention, which is constructed by computing a softmax over the dot product between each of the q and t values. This is then used to produce our yt output. Unlike with a linear recurrent neural network, we need to remember every previous k and v value in order to compute the next yt value, and these need to be stored in our kv cache. That being said, transformers are still the best model for basically every language modeling task. Over the last couple months, we've generously been donated very large and powerful open source transformer large language models. The goal of this paper will be to utilize these large transformer language models to produce very strong linear RNN models for inference. Specifically, in the first part of the talk, we'll discuss the problem of distilling a linear recurrent neural network from a powerful transformer model. Specifically, we're going to use the Llama models to distill an accurate and fast Mamba model. We'll be working with models at the 7 billion parameter scale. In the second part of the talk, we'll discuss methods to accelerate these Mamba models even further. Specifically, we'll look into using speculative decoding algorithms targeted to linear RNNs. Cool. So let's start by talking about distillation. So to briefly review distillation, we're going to start with a teacher model, in this case Llama, and we'd like to distill the parameters of a student model. To do this, we're going to set up an objective function to try to get the student model to match the predictions of the teacher. There are two popular ways to do this. One is to have the student model directly try to match the logits of the teacher model. This was used, for instance, in the Llama 2 models released this summer. The other approach, which I found works quite well, is to have the teacher model simply produce output sequences, and then have the student model learn from these sequences. This approach works particularly nicely in settings when you're conditioning on some input prompt X. You can think about this approach corresponding to the Microsoft Phi series of models. The most common use of distillation is to try to produce a smaller student model from a larger teacher model. However, there's a long history of also using distillation to move between model classes. Since distillation primarily works at the objective level, we can use whatever architecture we want in our student model. Perhaps more interestingly, though, there's a question of how we initialize our student model. A lot of work in NLP has shown that effectively initializing the student can make distillation much more effective and reduce the amount of required training data. For example, in the popular Distilbert model, we're able to initialize the smaller version, Distilbert, from the larger model, Bert, by simply borrowing a subset of its layers. Our goal here will be to initialize our Mamba student model directly from the large Llama model. That way we can use much less pre-training data in order to distill the new model. To bridge between the teacher and the student, we're going to be using a mathematical relationship that's been explored in a lot of recent papers on recurrent neural networks. Specifically, we're going to be using the idea of linearized attention. So to see this relationship, we're going to start with the standard attention formulation. This is basically the formula you've probably seen many times. It corresponds to the KQV relationship underlying standard transformer attention. The main thing to know about this equation is that there is one nonlinearity. That's the softmax function, which transforms the dot products between queries and keys into a distribution, basically normalizes them and puts the values between 0 and 1. If we remove this nonlinearity, everything on this slide is now just linear functions. This gives us the freedom to move things around. With a little algebra, we can compute the output yt as a function of the query times a sum over the previous k times v values. This new equation is exactly the form of a linear recurrent neural network. Here's what this looks like in pictures. On the left-hand side, we have the standard Llama attention. This corresponds to a softmax over the dot products between our q vector and all the previous key vectors. This is then multiplied by our value vectors in the output. If the softmax is removed, we can rearrange exactly these terms into the linear recurrent neural network, which is used by Mamba on the right-hand side. There's in fact a direct mapping between the keys here and the b values, the queries here and the c values, and finally the values v and the inputs x. Of course, this relationship only applies if we've removed the softmax from attention. Removing this softmax produces a much weaker form of this function and significantly degrades the accuracy of our model. However, when we use modern linear recurrent neural networks, we don't just have one recurrent neural network. We have a whole matrix of recurrent neural network states. These can compute all sorts of different forms of linear relations and make up for the fact that we may have a degraded version to start with. Our goal in this paper is to initialize our linear recurrent neural network with the linear attention form, but then allow it to learn to expand these dimensions to capture some of the complexities back of the original attention value. The main point of using the relationship is that we can do this by adding minimal additional parameters. Basically, we can start with the linear version of attention. It's going to be an approximation of our original computation. But that's okay, because we have a lot of additional capacity that can learn back the complexities that we've lost. Let's make this a little bit more tangible by looking at how we initialize the model. So here's a picture of our teacher model. This is a standard transformer. It's going to have two components, the multi-headed attention part, as well as the feed-forward neural network part. Throughout distillation, we're never going to change the feed-forward neural network. It will be frozen. We're going to focus on trying to recover the abilities of multi-head attention. We'll do this by transferring the orange parameters to our student model and fine-tuning them on the distillation objective. Specifically, our student model will look like this. As noted earlier, the keys, queries, and values can be transferred into Mamba, and worst case, they act like linearized attention. In addition, Mamba has several extra parameters, which will describe how to utilize B, C, and X to create the expanded dimensions in our hidden state. These parameters A and delta allow Mamba to create higher dimensional transformations that can be used to approximate some of the structure that we lost by removing softmax. At the end of the day, our student model is going to look surprisingly similar to the original transformer model. Again, all the orange parameters are transferred directly, all the blue parameters are transferred and frozen. The only new parameters are these green parameters, which represent a trivial portion of the total amount of parameters of the model. To actually do the distillation itself, we're only going to use 20 billion tokens. We're not going to use any pre-training tokens, but instead utilize the standard SFT and DPO training splits that are generally used for post-training of these models. The way we'll do distillation itself is we'll start by removing about half the attention layers, and then go to about 25%, and then continue adding more Mamba layers as we need them. In this way, we're able to piecewise replace attention with Mamba as we go. In the second half of the paper, we look at ways to even more efficiently run this new Mamba model. In previous works, authors have shown that Mamba is about 5 times faster in terms of throughput than a standard transformer model. Here we'll look at approaches to even further speed up this model in practice. So we're going to focus on the use of speculative decoding, and in particular, the challenges of applying speculative decoding to linear recurrent neural networks. Let's do a quick summary of how speculative decoding works. In this setting, we're going to have a very fast draft model, as well as a verifier model, which will be the main model we're interested in generating from. The assumption of speculative decoding is that generating directly from the verifier would be bottlenecked by waiting for the next token. If we can instead produce a very quick draft, we can verify it more quickly in parallel. In the example in the slide, the draft model gets a lot of the early parts of the document correct. When the verifier looks at these, it approves them and says, this is something I would have generated. But then the draft model, which is a much worse model, goes completely off track. The verifier gets to that part and is able to say that it would not have generated that, and tells the draft model to basically go back and produce something different. Again, the core assumption is that the verifier has 2 modes, and that it's able to run this parallel mode faster than it would be able to run the serial mode of generating. When using a transformer as the verifier, things work quite nicely. In order to verify a very long document, we're going to generate all the standard key values that we've discussed earlier in the talk. If the draft model was correct, we have the necessary key values we need to continue forward. If it's incorrect, we can rewind back in time by simply throwing away the most recent key values. In this case here, the red text is wrong, and so those key values can be dropped from the cache. Interestingly, the same properties that made it efficient to utilize linear RNNs also make them hard to use with speculative decoding. The challenge is that for linear RNNs, the whole state of the model is in this one hidden matrix H. And so if we get to a point where things are wrong and we need to rewind, we basically can't. We haven't cached all the previous hidden states. That was in some sense the whole advantage of this approach. Even more so, in the parallel mode for linear RNNs, we're going to try to avoid even creating many of the intermediate hidden states. This is an advantage for running these approaches efficiently, but here it doesn't give us access to the hidden states we need to rewind to. To get around this issue, we're going to develop a new kernel. This kernel is somewhere in between the fully parallel kernel used for training linear RNNs and the efficient inference kernels used for generation. The way this kernel works is it will generate a fixed number of tokens in parallel and maintain just enough hidden state information to allow us to do speculative decoding. Even at this small scale, verifying tokens in parallel will be very advantageous. The graph on the right shows that we're getting large speedups for even parallelizing just 4 tokens at a time, as opposed to step-by-step verification. Given this kernel, now let's look at how we do speculative decoding. To start out, our draft model will produce 3 tokens, which we show here in blue. After producing these tokens, we'll send them to the verifier. The verifier is a linear recurrent neural network, so it starts with its hidden state at position 0. It then verifies the tokens that it was sent. Note that it doesn't update its hidden state, because it doesn't know how far it's going to get before it finds an error. In this case here, it's able to verify 2 tokens until it finds an error. Specifically here, it's able to verify that one of the tokens from draft was correct, and then it was able to correct its second token for free. It then sends back the 2 good tokens to the draft model. Starting from these 2 good tokens, the draft model generates 3 more draft tokens. These are again sent to the verifier. The verifier hidden state is still at position 0, but it's now aware that the first 2 tokens it's seen have already been verified. Therefore, we can tell our kernel to do 2 things. Try to verify these 5 tokens, but worst case, checkpoint a new hidden state after the first 2. This leads to the following state. We were only able to produce 1 more verified token before failing, but using that compute, we were also able to advance to hidden state 2, which we know is already verified. We then go back to our draft model and run verification again, and this time we get lucky. All the tokens verify. In this case, we don't have to mess around with moving our hidden state to some intermediate position. If everything verifies, we can just move the hidden state all the way to the end and proceed. Okay, so let's look at some experiments. We looked at several different models in this paper. The main model we worked with was Llama 3, the 8 billion instruct model. At the time of publication, this was the best open source model available to us. We also ran experiments with the Zephyr 7 billion chat model. For baselines, we compared to a bunch of different hybrid Mamba models, as well as pure Mamba models that were trained entirely from scratch. Our argument is going to be that we're able to distill a version of Mamba that's better than a model that was trained entirely on trillions of tokens. And we can do this with relatively little compute. As noted earlier, we're only going to train on 20 billion tokens, although obviously our teacher model was trained on many more. The first set of benchmarks we look at are the standard chat benchmarks. These consist of mtbench and alpaca eval. Our baseline model here is the teacher model, our Llama 8B instruct model, which gets a score of 8 on mtbench and 22.9 on alpaca eval. Here we train 2 different versions of our hybrid Mamba student model, one with 50% attention layers and one with only 25% attention layers. We include results both from the standard Mamba model as well as the Mamba 2 follow-up. In both cases, the 50% model is competitive or performs even better than the original Llama teacher model. At 25%, it remains competitive in alpaca eval, although it performs slightly worse on the mtbench dataset. Next, we compare our distilled versions to Mamba models that were trained from scratch. The first 2 lines in this graph represent the TRI pure Mamba 7 billion parameter model, as well as the NVIDIA hybrid Mamba 8 billion parameter model. Our hybrid models with 50% attention perform better than both of these models. Again, that's only with 20 billion parameters of additional training. When we move to 25% attention, both of our models still outperform the TRI model, and our Mamba 2 variant even outperforms the NVIDIA hybrid Mamba 8 billion parameter model. We include many other benchmarks in the paper. For example, we find that our models are competitive with recurrent Gemma 9 billion on MMLU, and actually significantly outperform this model on other datasets. In fact, even our 25% attention models seem to perform at par with recurrent Gemma and Falcon Mamba 7B. Part of this is just the fact that we start with a very good teacher model, but it's also impressive that these models are able to learn so much from a different architecture. Finally, we find that we're able to get very large speedups using speculative decoding, which would not be possible simply applying standard kernels to linear RNNs. With a 2.8 billion parameter model, we're able to get about a 1.7 times speedup. With a 7 billion parameter model, we're able to get about a 2 times speedup. In the paper, we discuss all the various technical details required to get these models working on different hardware, as well as with hybrid models. Finally, I want to shout out one other concurrent work, which is the paper Transformers to SSMs, Distilling Quadratic Knowledge to Subquadratic Models. This is another approach to distill from transformers onto linear RNNs, and it actually takes a relatively different technical approach than discussed in this paper. I'll include a link below, definitely worth checking out. So I think, like a lot of people, I'm excited about this world where we can get language models to just solve a lot of very hard problems. I think this is going to be a combination of learning and search, and I think we should take seriously this idea that to do the most amount of search possible, we need architectures that take this seriously. In this work, we took a step towards distilling very smart models trained on tons of data into efficient models that are designed to handle long or very long contexts. I think there's still a ton to be done here, both on the algorithms, hardware, and architecture side of the equation. So good luck, and thanks for listening.